Good morning. Hope everyone is doing well. How come Claremont High School doesn't have a senior prank? You know, you guys should have a senior prank, I think. Wouldn't that be fun? I have an idea for a senior prank. I don't think it would work this year, but I think it would work next year. And so if you're a junior, I want to see you realize this prank. I'll talk to you about it in the Zoom room. All right, so I think I'm going to get started. So, all right. So this is CHL 415, period 5. I'm going to make this lesson pretty quick today because I have a lot to talk to you about in the Zoom room regarding returning to class on Monday. So, but this is a pretty straightforward lesson. And so what we're going to be talking about is Kirchhoff's laws. Okay? And so there are two Kirchhoff laws. So the first Kirchhoff law is called Kirchhoff's current law. All right, which I will call KCL. And Kirchhoff's current law says that the sum of the currents in a junction has to equal 0. So when I say a junction, I mean a meeting of wires. So let's suppose that I have, or another way you could think about Kirchhoff's law is the sum of the currents going into a junction equals the sum of the currents going out of the junction. So let's suppose I have 10 amps going into a junction. All right. And then I have 2 wires going out, and maybe this one is 8 amps. Okay, then this one would have to be 2 amps. All right, so the current going into the junction is 10. The total amount of current going out of the junction is also 10. So how you would express this in terms of a mathematical equation, you could say if the current is going into the junction, it's positive, and if it's going out, it's negative. And so you would have 10 minus 8 minus 2 equals 0. Okay? Kirchhoff's current law is a reflection of conservation of charge. Okay, so this is, sometimes you see exam questions that say, why is Kirchhoff's current law true? And it's because of conservation of charge. So if you have more current going into a junction than is going out of a junction, then that means that charge is building up at the junction. And as we know, like charge repels itself, and so you would have a lot of electrical repulsion happening at the junction. So that just doesn't happen. Okay, so the charge that goes into the junction is equal to the charge that goes out. If there was an imbalance, then that would mean that charge is collecting at the junction, which can't happen because of electrical repulsion. Okay. The second of Kirchhoff's laws is a little bit trickier. It's called Kirchhoff's voltage law. All right. So I will abbreviate that as KVL. All right. And what it says is the sum of the voltage changes around any loop has to equal 0. Okay. So for example, what if we had maybe we have a two resistors here, something that looks like this, and maybe another resistor. And so maybe I'll call this resistor 1 and this resistor 2. Maybe this is a 10-volt battery, and I'll call this resistor 3. All right, so we can imagine going around this loop. All right, and as you go through the battery, you rise 10 volts, and then you drop a certain number of volts across resistor 1, and you drop a certain number of volts across resistor 2, and then you get back to where you started. So the Kirchhoff's voltage law equation would be 10 minus V1 minus V2 equals 0. Okay. Similarly, if I go around this outer loop, I'm going to have a rise across the battery and then a drop across resistor 3. So that says that 10 minus V3 equals 0. And those are the only two things along that loop. So Kirchhoff's voltage law. And so Kirchhoff's voltage law is a reflection of conservation of energy. All right. Because as we know, the change in potential energy is equal to the amount of charge times the change in voltage. So imagine that you were an electron that is going around this circuit, and you're doing loops, right? These electrons are basically doing laps around the circuit. And if you made it completely around the circuit, then you had better have delta U equals 0, right? Because the reason is that if you didn't have delta U equals 0, then that means that you are just gaining more and more energy each time you go around the loop. And that's not what's observed, because circuits are in what is called steady state. So the properties of the circuit are not changing as time goes on. So it doesn't make sense for the electron to keep gaining energy, and that's not a steady state. It's a buildup of energy. And so because the left-hand side has to be equal to 0, the right-hand side also has to be equal to 0 as you go around that loop. Okay? So I was counting yesterday while I was running yesterday. I was counting, like, how many different techniques of circuit analysis do I know? And I think I know. I counted 5 different techniques. All right. I know it. So the one I'm going to teach you today is called node analysis. All right. So this is solving circuits with multiple batteries and multiple resistors. Okay? So what I taught you to do last time was I taught you to solve a circuit with just one battery. All right? But what if we have multiple batteries and multiple resistors, okay? Or other things. You could have transistors. Next week we're going to learn about capacitors. So you can have capacitors. You can have all kinds of different things, all right? So how do you solve these circuits? So yeah, this is a thing. I'm gonna yawn. So there are a couple of techniques. Like I said, I think I know 5 different techniques, because when I went to college, I started out as an electrical engineering major, and they just throw a bunch of techniques at you. So there's, node analysis, which is the one that I am going to teach you. There's one called mesh analysis. There's one called Thevenin equivalent. There's one called Norton equivalent circuit. There's one called superposition. So there's probably even more, but the point is that there's a lot of circuit analysis techniques that all will give you the same answer. This one that I'm teaching you is the most general, okay? So sometimes one of these other ones might get you an answer faster. This isn't the fastest way to get an answer, but it, is the most sort of regular. It always works the same way, all right? So that's kind of nice. So let me show you what I mean by like a more complicated circuit. So let's say I have battery. resistor, battery, then I have resistor, battery. All right, so this has 3 batteries and 3 resistors. These batteries are, let's say, 20 volts, 10 volts, and 5 volts. This is 15 ohms, this is 7 ohms, and this is 4 ohms. Okay. So now the first thing you want to do when you are solving this is you want to identify how many independent or how many different currents are there. All right. And so this problem has 3 branches to the circuit. So like if you just forgot about the resistors and the batteries and stuff, and you just replaced them with wires, how many different wires would you need to build this circuit? That's how many different currents there are going to be. So, there's going to be a current that flows along here. There's going to be a current that flows along here. And there's going to be a current that flows along here. Okay? So that's 3 currents. So I'm going to give them names and directions. So the first thing I'm going to do is I'm going to label the currents. All right, so I'm going to call this current, and you are going to give them directions. Those directions are completely arbitrary. Okay, so this battery, the positive terminal is here. So I'm expecting that it is going to push current out of its positive terminal. So that's why I'm calling this the sense of I1. Okay. Similarly, this this battery has its positive terminal. Okay. Right here. So it's going to push current in that direction. So I'm going to call that I2. And again, I might guess this wrong. But what I think is going to happen is that these 2 batteries are going to push current out of their positive terminal. Those 2 currents will meet together, and then they'll combine to make a big current that goes down through this 5-volt battery, because this 5-volt battery is the smallest battery. So I kind of think that these 2 batteries are going to dominate that battery and actually have its current going the reverse sense. But let's just say I didn't know that. All right. And maybe this battery is strong enough to shove current into both of the positive terminals for both of these batteries. That I'm not sure about. But I'm going to make a guess that this 3rd current is actually going this way, even though I'm almost certain that it is going to be going the opposite direction. So the point I'm making here is that the direction you choose the current to be is completely arbitrary. You just have to make a choice. All right? Then what you're going to do is you're going to label the positive side of each battery. Okay. So I've already done that. And then you need to label the positive side of each resistor. And the positive side of the resistor is the side that the current enters. Okay? And you do that according to your original assumption about the directions. Okay, so it doesn't matter if your guess was wrong, but you use that guess to label the positive side of that resistor. So I can see that I said that I think I1 is going around this way. So that means that the current is going into the left-hand side of this resistor. So I'm going to call that the positive side. All right. For I2, I said that the current was going upward. Again, I might be wrong, but I just used that guess as the basis for labeling the positive side. So it's going up, and so that means it's entering the bottom side of that resistor, so I'm going to call that the positive side. All right, and then here I'm saying that the current is coming around this way, so the current is entering the right side of the 15 ohm resistor, so I know its positive side. All right. So now what I'm going to do is I am going to write KVL for each loop. Okay. And so actually there are 3 loops in this circuit. I could do this loop. I could do the right side loop. Or I could do the big loop that goes around the outside. So that's 3 possible loops. So there would be 3 equations, but you are only going to write a KVL equation for each. I'm going to call it a minimal loop. Okay. So there are only 2 minimal loops. So I don't know if that's there. There is a mathematical term for that, but I can't remember what it is off the top of my head right now. So this is a minimal loop, and the right one is also a minimal loop. The big one around the outside is not a minimal loop because it has wires inside it. Okay. So let's go ahead and do that. So Kirchhoff's voltage law says the sum of the voltage changes around the loop equals 0. So your Kirchhoff's voltage law is going to be, so for the left loop, it's going to be 0 equals something. So I'm going to start right here, and I'm going to imagine walking around the loop. Okay? And so I'm going to walk around the loop, and then I hit this 20-volt battery, and I run into the negative terminal of that 20-volt battery. So I'm going to put negative 20. Okay? Then I continue around the loop, and then I run into the positive terminal of this resistor. So I'm going to put plus, and then the voltage drop across a resistor is IR, according to Ohm's law. That's what Ohm's law says, V equals IR. So the voltage drop is going to be the current that this resistor experiences times its resistance. So this resistor is experiencing I1 because it's in that branch of the circuit, and its resistance is 4. So I have plus I1 times 4. So now I continue along my loop. And you can see here that the positive side of this resistor is down low. So I encountered the negative terminal of that resistor. So I have minus. This is the current I2. So it's I2 times R, which is 7. Then I go bip, 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 bip. And then I encounter the positive terminal of this 10-volt battery. So I have plus 10. Then I go bip, 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 and I come back to where I started. So there's no more terms. All right. So this is Kirchhoff's voltage law for the left loop. So a couple of things. It does not matter where you start. If I started here instead of right here, then all that means is that this would be the first term, and then this would be the last term. So starting at a different point along the loop just shuffles around the order which term comes first and which term comes last. Okay? But that doesn't matter because addition, it doesn't matter which order you add things up. It also doesn't matter if you go clockwise or counterclockwise. Okay? Here I went clockwise around the loop. But if I had gone counterclockwise, I would encounter the opposite side of each circuit thing. So instead of encountering the negative terminal of the 20-volt battery, I would come around and encounter the positive terminal. So every term is going to have the opposite sign if I go around the opposite way. But because I'm setting that equal to 0, it doesn't matter, because if I just multiply both sides by -1, I get the original equation. Okay? So my point is that it doesn't matter where you start in the loop, and it doesn't matter whether you go clockwise or counterclockwise, you're going to get the same answer, the same equation. Okay? For the right loop, I'm going to start here, and I'm going to walk around it this way. So I go, and I run into the negative terminal of that battery. So I have 0 equals -10. Then I go through the battery, and I go, and I run into the positive terminal of the 7 ohm resistor. The 7 ohm resistor experiences current I2. So I have plus I2 times 7. All right. Then I continue, and I encounter this side of the 15 ohm resistor. That's the negative side. So I have negative. The current this is on the I3 branch. So I have minus I3 times its resistance, which is 15. Then I go, and I have run into the positive terminal of the 5-volt okay. And then I go, and I come back. I completed my loop. Okay? So notice how there are 3 unknowns here. There's I1, I2, and I3. So I need 3 equations in order to solve that. So the remaining equation, so I need one more equation in this case. That remaining equation is going to come from Kirchhoff's current law. So write KCL until you have the correct number of equations. So I'm going to write KCL for this junction right here. So KCL top junction. Okay. KCL top junction. So remember, KCL says that the sum of the currents going into the junction is 0. So we can just say that if it's going into the junction, it's positive. If it's going out, it's negative. Okay. So I can see that according to my according to my, kind of way of labeling the currents, all three currents are going into the junction. All three currents are going into the junction. So that means that they're all positive. So I have I1 plus I2 plus I3 equals 0. So now I have three equations for three unknowns, and I can solve this. It is customary to put the constant terms on one side and then the variable terms on the other side. So I'm going to rewrite this by moving the 20 and the 10 over to the left-hand side. So that's going to give me 10 equals, and then also normally we put the coefficient in front of the variable. So you have, 4I1 minus 7I2. Okay, for this one, I add the 10 over, I subtract the 5, so I have 5 equals 7I2 minus 15I3. And then I have 0 equals I1 plus I2 plus I3. So this is a system of equations for the three unknowns, and you solve it by your favorite method. Now, when I was in high school, we had to do this by hand. Okay, I can vividly remember doing these by hand my junior year of high school, and I actually enjoyed it. I like systems of equations. But now we have calculators and websites that can do all this stuff for us. So that's what I'm going to do. I'm going to go to Wolfram Alpha, and I'm going to, now Wolfram Alpha won't let me do I1, I2, I3, so I'm going to call I1 X, I'm going to call I2 Y, I'm going to call I3 Z. All right. And so let me, I guess this one. So here's Wolfram Alpha, and I'm going to put solve, and I'm just going to list all the equations. So 10 equals 4x minus 7y. So again, remember, I'm making the substitutions. I1 is x, I2 is y. 5 equals 7y minus 15z, and then 0 equals x plus y plus z. So those are the three equations. I just typed them in. So now let's see what Wolfram Alpha can do it. So it is solving them correctly. I'm going to do approximate form. Okay, so it says that x, which was I1, is plus 1.32 amps. I2 is negative 0.67 amps, and I3 is negative 0.65 amps. Okay. So I wrote that down. Okay, so what this means is I actually guessed, so these ones are negative. So all that means is that I guessed the direction of I2 and I3 incorrectly. That's all that means. Okay, so you don't have to panic. It just means that both of these currents are actually going downward, okay, instead of upward. So that's no big deal. I'm trying to think. Excuse me. So then we can use this information to solve for whatever we want to solve for. Maybe we just are solving for the current. That's completely fine. But I could say something like, I don't know, what is the voltage drop across the 7 ohm resistor? All right. And if I look at the 7 ohm resistor is experiencing current I2. So if I say V equals IR, so it's experiencing I2, so that is negative 0.67. If we just want what is the magnitude? I'll just say the magnitude so that it is, so I don't have to worry about the sign of the current, 0.67 times its resistance, which is 7. So that many volts. Okay. I don't really care what the actual number is. What if I said, what is the power dissipated by the 4 ohm resistor? Well, in that case, power is IV. V is IR, so the power is actually I squared R. And this 4 ohm resistor is experiencing the current I1. So I1 is 1.32. So I have 1.32 1.32 and then squared times its 4 ohms, so times 4. So that many watts of power. Let me just walk you through one more because I'm not going to actually solve it, but I'm just going to talk about it briefly. What if I had like a 3-loop circuit like this? Okay, so how many different currents do you have? Well, you would have one current for this branch. You would have a second current for this branch. You would have a third current for this branch. You would have a fourth current for this branch. You would have a fifth current for this branch. And then you would have a sixth current for this branch. Okay? So you would need 6 equations. All right. So I'm obviously not drawing the resistors or the batteries. Now, how many minimal loops are there? Well, there are 3 minimal loops. Okay. So there's that loop, there's that loop, and there's that loop. So you would get 3 KVL equations out of that. But because there are 6 variables, we need 6 equations. So the remainder of the equations would come from Kirchhoff's current law for any 3 of the junctions. So maybe I could write an equation for that junction, an equation for that junction, and an equation for that junction. And I wouldn't need to do that junction because that already gets me enough equations. So I would have 3 KCL. Okay? So solving a system of 6 equations is quite extensive. So you really want to learn how to do this on your calculator is the best way. Okay? You can look it up on YouTube to figure that out. All right, that's my lesson